All right, for chapter 4, we're talking about covalent molecules or molecular compounds, covalent or molecular compounds. So we're going to look at drawing Lewis dot diagrams in this video. And then we'll also looking at chemical equations, how to write those. Okay, so when we're looking at a covalent compound, or we can also call that a molecular compound, we're looking at elements, or the elements in those compounds are only nonmetals. So nonmetals bond with nonmetals, or nonmetals can bond with metalloids. Sometimes that exception comes up in Alex. But most of the time it's just nonmetals and nonmetals. And these elements share electrons to achieve a complete octet. And remember, hydrogen and helium only want 2 electrons, so those are exceptions to our octet rule. Everything else would like to have a full 8 electrons in their valence shells. So I wanted to show you in Alex. Let's see if we go to Alex. In chapter 4, we can look. Chapter 4 has 12 topics. And as we go through these, we can use the periodic table. And remember, this will show you, so the blue ones are metals, these green ones are metalloids, the yellow ones are nonmetals. So we can, if we have a compound, we can decide if it's covalent by looking at the element and deciding, if it's metalloids and nonmetals only, then that's going to be a covalent, or they call it a molecular compound. If it's only yellow, that's nonmetal, that's covalent. If there's any metals, anytime you see a metal, that can't be a covalent compound. Okay, these are interesting. We're starting to get into molecules with carbon. Those are interesting to us because we are made of a lot of covalent compounds. So that's kind of interesting. I know that's interesting to some of us. Okay, so we need to remember how to draw Lewis dot diagrams for atoms. So the first thing that we need to do is look at the number of valence electrons around each of these elements. And so I think the easiest way to do that is to look at this periodic table and remember that we can, as we move across the periodic table, skipping the transition metals, we can just count how many valence electrons there are. So this column, everything in this column has 1 valence electron. Everything in this column has 2 valence electrons. These are more complicated, so we're skipping those for this class. This column has 3 valence electrons, 4 valence electrons, 5, 6, 7, 8. Okay. So if we look at the number at the top, these 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, that's telling us the number of valence electrons. So you don't even need to put that on your note card. Maybe you need to remind yourself to look there, but you don't have to remember how many valence electrons because this periodic table is going to tell you, and you can use this on the test. So you just need to remember how to find how many valence electrons. Okay, so our examples, we have phosphorus, sulfur, carbon, iodine, hydrogen, and argon. So I'm going to write those down on my whiteboard. And then all we need to do is we need to look up how many valence electrons there are. So hydrogen has 1. Okay, I'm going to go between my whiteboard. So hydrogen has 1, so I just need to put a dot. Okay, argon is clear across the periodic table. Where are we? Argon is over here. It has 8 valence electrons. And so to draw those, I'm going to draw 2 dots on each side. Okay. Anytime we have a lone electron, that's going to want to pair up, and that's going to tell us how many things that atom wants to bond with. So hydrogen, this is our quick tip, hydrogen wants to bond with only one other thing. So it will form 1 bond. Okay, these are our rules. There's a few times that they get broken, but generally these are our rules for our class. Okay, let's go back to our periodic table. Yeah. Okay, so let's do phosphorus next. Phosphorus, find that's here. So that has 5 valence electrons. So we'll go back to our whiteboard. phosphorus has 5, so I'm going to do 1, 2, 3, 4, 5. Okay, so let me show you another way to do this. So I just know that phosphorus wants to form 3 bonds, but we can go like this: 1, 2, 3, 4, 5, and then I have 3 lone electrons. We're gonna keep them unpaired. The electrons don't like to share space if they don't have to, so we're gonna keep them unpaired, and then if we have to put them together, we will. And so that's probably a better way. So do 1 on each side and then go back around. So now we have 5 valence electrons around phosphorus. We know that because of the periodic table. We know there's 5. And then we can count the lone electrons. Phosphorus wants to form 3 bonds, generally. Okay, so I want to find 3 other things to bond with. Okay, let's look at sulfur. Where is our periodic table? Sulfur is here. That has 6 valence electrons. So let's go back to our picture. So 1, 2, 3, 4, 5, 6. And then we have 2 lone electrons. This wants to form 2 bonds. Carbon, where is carbon? Is here. It's in the 4A column, or column 14. So it wants to form 4. Oh, it has 4 valence electrons. So let's go back to our 1, 2, 3, 4. And we have 4 lone electrons, so we want to form 4 bonds. Generally, carbon wants to form 4 different bonds. And the last one we have as an example is iodine. Iodine is here. Iodine is in column 17 or column 7A. Generally, let's see. We have 7 electrons. 1, 2, 3, 4, 5, 6, 7. Generally, it wants to form 1 bond. Oops, I didn't switch back. Let me do that one more time. So iodine has 7. 1, 2, 3, 4, 5, 6, 7. It wants to form 1 bond right here. It'll pair up that lone electron. So remember, this is not the total number of electrons around. That's just the number of valence electrons. And so this model helps us to figure out how many things we should have bonding to each atom. All right, so then we have some rules for drawing Lewis structures for molecules. So we've drawn them for single atoms. Now we're going to look at drawing them for a molecule or a covalent compound. So what we need to do is figure out how many valence electrons there are in the total structure. Then we're going to draw a skeleton structure. We're going to pick a central atom. We have to decide which one's going to be the central atom. And then we're going to connect all of the atoms to the central atom. And some of these can get kind of tricky, but in general, they're the ones in our class are pretty doable. And then once we have our central atom and we've connected, then we're going to distribute the remaining electrons as lone pairs, and then we want 8 valence electrons, except hydrogen only wants 2. And then if there's any extra electrons, we're going to put them on the central atom. Then we're going to rearrange the atoms if we need to make sure that everything has 8 valence electrons. So if our central atom doesn't have enough, we can rearrange until we have an octet. Okay, so our first example is water. So let me pull up our whiteboard. So we have water. The first thing that we're going to do is count total valence electrons. So I need to figure out how many. I have 2 hydrogens and I have 1 oxygen, and then how many valence electrons. So let's go back to our periodic table in Alex. So hydrogen has 1 valence electron. Oxygen has 6 valence electrons. So let's go back to our whiteboard. Hydrogen has 2. There's 2 hydrogens, but they each have 1. There's 1 oxygen. Each of those has 6 valence electrons. So then we'll add this up. Okay, let's see. So we've got 2, 2 plus 6. We have a total of 8 valence electrons in water, H2O. So then we're going to pick a central atom. So the central atom is generally going to be the atom that there's only one of them. And then sometimes it gets tricky. So then we're going to look at electronegativity. Usually the atom with the least amount of electronegativity will go in the middle if there's multiple single type of atoms. So we'll look at that. So here we're going to pick oxygen to go in the middle. And then I'm going to bond the outer atoms to oxygen. So right now, every time I draw a bond, that's 2 electrons. So I've used 2 4 electrons. So I'm going to subtract that off my total and kind of keep a track of what electrons we've used. We have 4 electrons left. So we're going to fill in the outer orbitals, the outer atoms orbitals if we can. But hydrogen can see these 2 electrons because they're bonded to it. So any bonds attached to an atom, the atom can see those electrons. So right now, hydrogen can see 2 electrons. So remember, every time there's a bond, there's 2 electrons. Over here, there's 2 electrons. So hydrogen only wants 2, so hydrogen is good, hydrogen is good. Okay, so the rest of these 4 electrons we're going to put on oxygen. And then, if we count up the electrons around the oxygen, now we have 2 in this is called a lone pair. If we have 2 electrons by themselves not participating in a bond, that's a lone pair. 2, 4, 6, 8. So now oxygen is happy, and we've used 4 more electrons. We have 0 electrons left to show. Hydrogen's happy, oxygen's happy, hydrogen's happy. So this would be a Lewis structure for water. Let's look at the next example of drawing the Lewis structure. So we have NO2. So the first thing that we're going to do is we're going to look at how many valence electrons each of these has. So how many valence electrons does this nitrogen bring, and how many does these 2 oxygens bring? We have oxygen, and there's 2 of them. So remember, let's go back to our periodic table in ALEKS. So remember, we can just click on this ALEKS periodic table. We need to look at nitrogen. Oops. Nitrogen is in group 5A or column 15. And so it has 5 valence electrons, and oxygen has 6 valence electrons. So let's go back here. So nitrogen has 5. Each oxygen has 6, but there's 2 of them. So that gives us 6 times 2 is 12. We have 5 here. So we'll end up with an odd number of electrons. And this doesn't happen very often, but I'm going to try to show you what we do if that happens. So then the second thing, after we know how many total valence electrons we need to show in our structure, is we need to decide which is the central atom. So there's only one nitrogen, so we're going to pick that one as the center. And then we're going to connect the other atoms to the central atom. Okay, and then remember, every bond is 2 electrons, one from nitrogen, one from oxygen, one from nitrogen, one from oxygen. So 2, 4, we've shown 4 electrons. And so now we have 13 electrons left to show. All right, so the first thing that we're going to do is we're going to fill in electrons to satisfy oxygen, the outer atom. So we'll start over here. 2, 4, 6, 8, 10, 12. Okay, so now we've used 12 more electrons. We have 1 left. If we look here, we have 2, 4, 6, 8 around oxygen, 2, 4 around nitrogen, 2, 4, 6, 8 around this nitrogen. Oh, just 2 and 4 around nitrogen. So we have 1 left. These outer atoms are satisfied. So what we're going to do is we're going to put that lone electron on the nitrogen. And I'm picking nitrogen because it has the smallest electronegativity. Also, it doesn't have a complete octet. So if we go back to our periodic table, if we look at, if we click on the element, it shows us more information, and it tells us the electronegativity of nitrogen is 3, electronegativity of oxygen is 3.4. So oxygen is going to want to make sure that it's satisfied compared to nitrogen. Nitrogen still has a pretty high electronegativity, but compared to oxygen, it's a little bit less. So nitrogen is going to be more happy with not an octet if we run into a situation like this where we don't have enough electrons. Again, this doesn't happen very often. So let's go back to our example. But for this example, we can do one step better. What we can do is we can take electrons from one of these oxygens. It's symmetrical, so it doesn't really matter. I'm just going to pick them from the right side. And I'm going to move these two electrons between nitrogen and oxygen, and they're going to form a bond. So I'm going to redraw this. Okay, so now we have 2, 4, 6, 8 around the oxygen. So oxygen can still see both of these electrons. Now we have this double bond. This oxygen still has 2, 4, 6, 8. That's fine. This one has, and that nitrogen in the middle has 2, 4, 6, 7. And so that's the best that this nitrogen can do. And that's what we do if we only have an odd number of electrons. So the first thing that we need to do is decide how many total valence electrons there are. So we're going to look at how many does carbon have, how many does hydrogen have, times 2, and how many does oxygen have. So we're going to go back to our Alex periodic table. Hydrogen has 1 over here. Oops. Carbon is in this column. It has 4 valence electrons. Oxygen is in this column. It has 6. So let's go ahead and write that down. Carbon has 4. Hydrogen has 1. There's 2 of them. So we'll do that. So that's 2. And then oxygen has 6. So we have a total of 8 plus 4 is 12. 12 total electrons. Okay, so now we have to decide which of these is the central atom. So one thing that we can look at is if we draw the valence structure of each of the atoms with the electrons, we can tell how many bonds they're going to form. So carbon has 4 valence electrons if we draw it like this, 1 on each side. This tells us carbon wants to form 4 bonds. Hydrogen only has 1 valence electron, so we can put it here. It only wants to form 1 bond, and it can't be in the middle or central because it can only have 1 bond. You can't put it in the middle. Oxygen, we have 6. So we're going to go 1, 2, 3, 4, 5, 6 valence electrons. These lone electrons, again, those are the ones that are telling us how many bonds it can form. Because it has 2 lone electrons, if we draw it like this, it's going, let me fix this one. Let's put these over here. This has, it can form 2 bonds. So carbon is going to be our central atom. Often, if we look at a molecule and has carbon is going to be a central atom because it wants to bond to so many things. The other thing we can look at is electronegativity. And besides hydrogen, which can't be the central atom, a lot of the time the least electronegative atom will be the central. So if we look at carbon, it has an electronegativity of 2.6. Oxygen has an electronegativity of 3.4. So oxygen, that means oxygen is going to pull the electrons towards itself. And carbon is going to be nicer, I guess. It's going to share easier. It doesn't hold the electrons as tight. So if we put carbon in the middle, oxygen will get more of the electron density that it wants. So let's go back here. So if we see carbon, we're probably going to put it in the middle. So we've found our central atom, and then we're going to stick the other atoms around. So we have an oxygen, and then a hydrogen, and hydrogen. And right now it doesn't really matter where we put them. So remember, every bond has 2 electrons, so 2, 4, 6. We've used up 6 electrons. We have 6 electrons left to show in this structure, this Lewis structure. So the first thing that we're going to do is fill the outer atoms. So hydrogen doesn't want any more. It has these 2 electrons. We can draw like a... This is hydrogen can see these 2 electrons in the bond. Hydrogen doesn't want any more. This hydrogen also can see these 2 electrons. It doesn't want any more. So we're going to start by putting these electrons on the outer atoms in this oxygen. So we've got 2 here, 2 here, 2 here. 2, 4, 6. So now we've used up all 6 of our electrons. We have none left to show. So if we look at oxygen, oxygen has 2, 4, 6, 8 around it. So oxygen gets to see this bond, carbon gets to see this bond. And this carbon in the center gets to see 2, 4, 6. So what we're going to do is we're going to take 2 electrons from the oxygen and we're going to shift them between carbon and oxygen. So we're going to have a double bond between carbon and oxygen. So then this is our structure. So we can check. So at the end, we should always check the valence electrons. Remember, trying to get 8 unless it's hydrogen. Hydrogen only wants 2. So this hydrogen has 2, this hydrogen has 2, this carbon has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. So remember, if the bond is connecting to that atom, it can see all of the electrons in that bond. So everything is satisfied. So that's our our Lewis structure for CH2O. Okay, let's do the next example, which is OH minus. So sometimes we're going to have to look at the Lewis structure for ions. So this is hydroxide. So what we do is if we see, let's see, there we go, we can see that. If we see this minus charge, that just means this tells us add an electron to your structure. So, because we have an extra negative charge. Remember, electrons have a negative charge, just a little bit backwards. If we have a negative charge, we're adding an electron. That's a little confusing. Okay, so we've looked up oxygen has 6 valence electrons. Hydrogen has 1. We just looked that up, but we can always look that up again in the Alex periodic table, even on the test. If we add this up, we have 7. And then remember, we have this minus charge, so we're going to add 1 more. So we have a total of 8 valence electrons that we need to show in this hydroxide structure, OH. So I'm going to put OH. It doesn't really matter which ones. There's not a central atom if there's only 2. They just have to connect. So right now we've used 2 to connect them. We have 6 left. Hydrogen doesn't want any. We're going to stick the other 6 on oxygen, 2, 4, 6. And then to show that we have an extra electron in the structure somewhere, not from the hydrogen or the oxygen, we're going to put a negative charge. And that matches the formula. We have a minus charge on the formula. We have a minus charge on the Lewis structure. So that's hydroxide. The next one we are going to do is NH4+. So can you guess if we have a minus charge, we're going to add an electron. If we have a plus charge, what do you think we do? We're going to take away an electron. So if we have a cation, NH4 is ammonium. Just tip it a little bit. Okay, NH4+. This is telling us to take away an electron. So if we had 2 plus charge, we would take away 2 electrons. We just have a plus charge, 1 plus. Okay, so we're going to take nitrogen and look up how many electrons that. Valence electrons, not total electrons. And then hydrogen. Hydrogen has 4. There's 4 of them. Nitrogen has 5. So that's a total of 9. But because we have this plus charge, that tells us to take away 1 from, because of our plus charge, 1 electron from our structure. So we have another 8 electrons we have to show in our structure. And we're going to pick nitrogen as our central atom. There's only 1 nitrogen. And we have 4 hydrogens, so they're just going to go around the nitrogen. And then if we count up the electrons, we have 2, 4, 6, 8. So we've used up all 8 of our electrons. We have no more to show. And we need to show, just like we did in the anion, we need to show that this has a positive charge. There's 1 less electron than nitrogen and hydrogen brought in their valence shell. Okay, so these are some to practice. So go ahead and practice those. All right, let's go over these examples. So we have CCl4. So the first thing that we're going to do is count total valence electrons, and we find that on the periodic table. So carbon has 4, chlorine has 7, and there are 4 chlorines. So that gives us 28 plus 4 is 32. There's no ion, so we don't have to add or take any away. So we're going to pick carbon. Carbon is a good central atom. Also, there's only one carbon. So if there's only one of those atoms, we're going to pick it as a central. And then we're going to put Cl, 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 Cl. Okay, that's 2, 4, 6, 8 valence electrons. So this gives us, what is that? 24 electrons left. And then we're going to, well, I think that's right. We're going to put the rest of these around the outer atoms first, and then if we have extra, we can put them on the central atom. So I'm going to put 2, 2, 2, 2, 2, 2. I'm going to put them as lone pairs. These are lone pairs. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've used up all of our electrons. I don't know what that is. And now we have no valence electrons left. So we need to check to make sure that every octet is satisfied. So chlorine, and they're all the same. So I'm only going to check one. So this chlorine has 2, 4, 6, 8. You can see all of these electrons. So that's good. And then carbon in the middle can see all of the electrons in all of these bonds. So 2, 4, 6, 8. So that carbon is also satisfied because this chlorine matches all of these. Then they're all the same. They are all satisfied. So this would be our Lewis structure for CCl4. Okay, the next one we're going to run through is CO3 2 minus. So carbon has 4 valence electrons, oxygen has 6, and there's 3 of them, so that's 18. And we have 18 plus 4. It's 22. And then this tells us, this anion, 2 minus, tells us we need to add 2 more to our electron count. So now we need to show 24 valence electrons in our structure. We're going to pick carbon as the central atom because it's carbon, and because there's only one of the carbons, there's 3 oxygens. And then we're going to just connect the oxygens to the central atom, and then we're going to start filling these 24 electrons around the outside. So 2, 4, 6, 8, 10, 12, 14. Oops, just a second. So we use electrons to connect these bonds. So let's go back here. So we've got 2, 4, 6. So let's subtract those 6 off. That gives us 18 left. Okay, now we'll place it in 2, 4, 6, 8, 10, 12, 14, 16, 18. There we go. So now we've shown all of the electrons. This oxygen, let's check this one. We have 2, 4, 6, 8. That has a satisfied octet. All of the oxygens are the same, so they must also all have a satisfied octet. Let's look at carbon. This carbon only has 2, 4, 6. So one of these oxygens needs to share. So I'm just going to pick this right one. We're going to take these 2 electrons. We're going to skew them here. That will be a double bond. So we'll have oxygen, carbon, double bond oxygen with 2 lone pairs, oxygen. So now we have around this carbon 2, 4, 6, 8. This oxygen still has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. So if it's touching the bond, it counts those electrons. So that's our Lewis structure for, we need to show that it's an ion. So in here we have 2 extra electrons, 2 minus. CO3, 2 minus. Okay, the next one is COCl2. Carbon has 4 valence electrons, oxygen has 6 valence electrons, chlorine has 7, but there's 2 of them. So 4 plus 6 is 10. 10 plus 14 is 24. Okay, there's one of oxygen, there's 1 carbon. I'm going to pick carbon as a central atom. Carbon has a smaller electronegativity, so carbon's going to go in the middle. I'm going to connect oxygen and chlorine. It doesn't matter too much how they're arranged in a Lewis structure, as long as they're connected to the central atom. we've got 2, 4, 6 minus 6, we have 18. So this one kind of seems like the one we just did. Then I'm going to stick these 18 electrons around the outer atoms to fill their octets. 2, 4, 6, 8, 10, 12, 14, 16, 18. Now we've shown out all of the valence electrons. This one's not an ion. Then we have to decide which of these are we going to take electrons and share with carbon. Well, if we look at the lone electron, the lone valence, lone atom, oxygen has 6 valence electrons, chlorine has 7 valence electrons. So chlorine has 1 lone electron, oxygen has 2 lone electrons. Oxygen wants to form 2 bonds, generally. Chlorine wants to form 1 bond. So we're going to take the electron pair from oxygen and move it to chlorine. And this also has to do with electronegativity. Chlorine has a greater electronegativity than oxygen, so oxygen is going to have an easier time sharing its electrons than chlorine. Chlorine needs to pull its electrons tight, and it can't share as well. So we're going to take this and move this electron pair down as a double bond, and that will help us satisfy the octet for carbon. That's chlorine. Okay. So now if we look at this, we have chlorine has 2, 4, 6, 8. Chlorine has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. And oxygen can see 2, 4, 6, 8. So all of them have a satisfied octet. This would be our Lewis structure. Okay, and then the last one on here is CH2Cl2. So carbon has 4, hydrogen has 1 each, but there's 2 of them. Chlorine has 7 each, and there's 2 of them. So let's see, we've got 4 plus 2 plus 14. That's 20. Does that seem right? Okay. So we're going to stick carbon in the middle. Carbon's a great central atom. And then we're going to stick the other elements around the central atom. And then we've used 2, 4, 6, 8. We have 12 left. We're going to stick those 12 around chlorine. These chlorines, because hydrogen already has its 2 electrons in the bond. 2, 4, 6, 8, 10, 12. Okay, we've used all 12. Perfect. And then we just check octets. So hydrogen has 2 electrons. It has a satisfied octet. Carbon has 2, 4, 6, 8. It has a satisfied octet. Chlorine has 2, 4, 6, 8. It also satisfied. So everything has a correct number of electrons. This would be our Lewis structure. Some of these have. Okay. Let's go back to our slides. So one of the Alex topics asks us to predict or to look at this and see how many bonding pairs and how many lone pairs. So a bonding pair of electrons is just a bond. So we're counting bonds. How many bonds? How many lone pairs? So if we look at, it tells us which atom to look at. So if we're looking at nitrogen here, this nitrogen would have 1, 2, 3, 4 pairs of bonding electrons, or bonds, 4 bonds. Okay. How many lone pairs does nitrogen have? Around nitrogen, there are no lone pairs. Okay, that's different if we're looking at this oxygen. If we look at this oxygen, it has 1, 2 bonds, so 2 bonding pairs, and it has 1, 2 lone pairs. So anytime there's 2 electrons on the side, that's a lone pair. So this oxygen has 2 lone pairs, 2 bonding pairs. Okay, then let's look at this. This is methanol. It's saying look around hydrogen, and sometimes I think the Alex question shows it like this. So if we have 2 electrons between them, that's a bond. So this would be 1 bond, and hydrogen has 0 lone pairs. Okay, so that's how you do that Alex topic. So go ahead and practice this. So if we're looking at this oxygen, how many bonding pairs? How many lone pairs? So here we have 1, 2 bonds, and we have 2 lone pairs on this oxygen. So it is going to tell us which atom to look at. Here we have chlorine. We're looking at chlorine. Chlorine has 1 bonding pair. So this is a pair. Anytime we see a bond, that's 2 electrons. So 2 electrons here is 1 bonding pair, 1 bond, 1, 2, 3 lone pairs. Okay, another topic in Alex asks us to check is the Lewis structure correct? So you just need to be able to critique it and decide if it's correct or not. So this is some rules that help me to do that Alex topic. So the first thing that you're going to do is look at the total number of valence electrons. If that's wrong, then the structure is wrong. And then it can have the correct number of valence electrons, but each of the atoms have to have an octet. So make sure you count, make sure each of the atoms has 8 electrons, and then, except hydrogen, obviously. Hydrogen only wants 2 valence electrons. And then anything in the third row or lower in the periodic table is large enough that it can actually fit more than 8 electrons. And we see this sometimes. And chemistry is kind of, we find these patterns and then there's always an exception. So these are some exceptions to the rule, the octet rule. Group 3 elements like boron, they can only fit 3 electrons around them. Or 3 bonds. So let's look at the periodic table. Where's our periodic table? Oops. I'll have to log back into that. Let's look at the periodic table for a minute. So this is the first row, and it says anything below the third row can accommodate something more than more than 8 electrons. So let's back over here. So this row, they can only have an octet. They're too small. They can't fit extra stuff around them. But once we get down to things like phosphorus and sulfur and chlorine, if the phosphorus is a central atom, phosphorus can accommodate 5 bonds. So that would be 10 electrons around it, or just because it's a little bit bigger of an atom. So this is where our exception for our octet rules breaks down. So if you see something like that, that's why. It's just a little bit bigger. And it does break the octet rule. Okay, so let's go ahead and look at these Lewis structures. So the first thing that we're going to do is count. Is the total number of valence electrons correct? And then we're going to check, does it have an octet? So let's look at this one. So if we look at this, carbon has 4 valence electrons, and then we have 1 each from hydrogen, hydrogen, hydrogen. So that would be 7. And then oxygen gives us 6 more. So that should be 13. So if we count up these electrons, we have 2, 4, 6, 8, 10, 12. So this is only showing 12 valence electrons. We should have 13. So this one is incorrect because the total number of valence electrons is wrong. And that's what the Alex topic will ask you, is why is it wrong? This one's wrong because it has a different number of total valence electrons than it should. Okay, let's jump down to this one. Nitrogen and nitrogen, they both have 5 valence electrons. And I can look at that on the periodic table. We can practice that. Nitrogen is in this column. The 15 reminds me that has 5 valence electrons. So 10 between the 2 nitrogens, and we have 2, 4, 6, 8, 10. So, okay, that has the correct shown total number of valence electrons. And then let's check the octet. So nitrogen has 2, 4, 6. So that doesn't have an octet. This nitrogen has 2, 4, 6, 8. So this oxygen satisfies the octet rule. The nitrogen over here does not satisfy the octet rule. So that's what I would say. I would say this is not a correct Lewis structure because the nitrogen doesn't have an octet. Okay, let's go over to this one. We have oxygen, sulfur, oxygen. They're all in the same column. They all have 6 valence electrons. We're here. So we should be seeing 18 total valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so we have the correct total number of valence electrons. And then let's go ahead and count octets around each of the atoms. So this oxygen has 2, 4, 6, 8. Sulfur has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. So this is a correct Lewis structure. It has the correct total number of valence electrons, and it has the correct octet for each element. Okay, let's jump over to this one. So this one, we would count up total valence electrons. So 4 plus 4 is 8, plus 6 is 8 plus 6 is 14. 15, 16, 17. 17 plus 7 is 24. So we should be seeing 24 total electrons. So let's count those up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that has the correct total number of valence electrons. And then the other thing we need to look at is octet. So hydrogen only wants one bond. It's got one here, one here, one here. So hydrogen's good. Chlorine wants an octet. So 2, 4, 6, 8 around it. Carbon has 2, 4, 6, 8 around it. This carbon has 2, 4, 6, 8 around it. And then oxygen, 2, 4, 6, 8. So this is a correct Lewis structure. And then let's jump down to this one. This one, phosphorus, is in the same column as nitrogen. So it should have 5 valence electrons. And we should see 10 total valence electrons. So 2, 4, 6, 8, 10, 12. So this is incorrect because it has an incorrect number of valence electrons. Okay, so let's go here. This is like an Alex topic where we are trying to predict the type of compound that would form with these elements. And so we can predict this because our different elements want to bond with different amounts of things. And we've kind of looked at this a little bit. So we're just predicting basically the formula or the Lewis structure for these. So when we draw phosphorus, it has 5 valence electrons. So it wants to bond to 3 things. Fluorine has 7 valence electrons. So it wants to bond to 1 thing. So what we can do is we can say, oh, well, this wants to bond with 3 things. This one wants to bond with 1. So we just need 3 ones to go with our 3. So this would be something like this, where we have. So this would be the compound that would be formed between P and F, phosphorus and fluorine. And our formula would be PF3. Okay, and then we can just do that because we know how many valence electrons these atoms have. Carbon has 4 valence electrons. Sulfur is right below oxygen. It has 6. 1, 2, 3, 4, 5, 6. So this helps. This is just helping us to predict bonding. So this one wants to form 2 bonds. This one wants to form 4 bonds. So we can also just like connect them. Oh, if I add 1 more sulfur, maybe we'll put the lone electrons on the carbon side. So sulfur has 6 electrons now. So if we had carbon double bonded to sulfur, oh, that's a weird S. Then this would be our predicted compound, and we'd have CS2. That would be what we would predict. Okay, nitrogen is like phosphorus. We can just interchange these. So nitrogen wants to form 3 bonds. Phosphorus wants to form 1 bond. So this would be NF3. That's our kind of our pattern. We can start seeing that these are very similar because we have the same number of valence electrons in these atoms. Okay, and then NO. Let's see, this one is a little bit weird. Okay, so we've got nitrogen has 3 valence electrons, or 3 lone, has 5 valence electrons, so it has 3 unpaired electrons. Oxygen has 6. So this is another one with an odd number of electrons, where we would probably say we would want to do, at least this one we'd probably do NO2, where we looked at that one before, where nitrogen ends up with a single electron on the top. So this one is tricky because we end up with an odd number of electrons. Okay, let's keep going in our slides. Okay, the last thing that we're going to talk about in this slide presentation is writing formulas. So if we go to the Canvas page for chapter 4, I guess in the module, chapter 4 module, there's some note sheets here that might help you. So if we click on this note sheet, it has the rules written down for you. So you can write these all down if that's going to help you, or you can reference this note sheet. And these rules are just from Alex. So this is what Alex is going to be looking for. And generally, this is really what we are doing as chemists also. Okay, so we've been practicing writing elements. So we have a capital and a lowercase. And then if we have more than one, we're going to use a subscript. And then let's see. Then this is the rules for writing those formulas. So we're going to write the formulas from left to right, except, like in chemistry, there's lots of exceptions, except for hydrogen. Hydrogen fits between group 5A and 6A. So it would be like carbon, nitrogen, hydrogen would fit right in between group 5A and 6A. And then we go to oxygen and fluorine. So again, so order is left to the right on the periodic table. Hydrogen should fit after nitrogen in our chemical formula. The other thing that happens is if they're stacked on top of each other. So, is that rule here? I don't see it. So I'm going to look at an example here. So if I have oxygen and sulfur in a compound, I'm going to put the bigger element first. So sulfur should go before oxygen. This is like spelling. We just make sure everyone's writing the formulas correctly in our chemistry world. So if sulfur and oxygen were in the same formula, we put sulfur first because it's bigger. So left to right, hydrogen fits between nitrogen and oxygen. And if it's in the same column, bigger goes first, then the smaller one. Okay, so let's go back here and we'll practice. So this one is alanine and methionine. These are some amino acids. So the first thing that I'm going to do is count up. Maybe I'll insert a text box. I'm going to count up how many of each atom there are. So I see I have carbon. Let me count those up. 1, 2, 3, 4. Oh, it's just 3, excuse me. 3 carbons. I'm going to do I'm just going to put the 3 here, and then I'll go back and fix the subscript. And then what else do we have? We have nitrogen. I see a nitrogen here. I see an oxygen. How many oxygens there are? 1, 2. I see hydrogen and hydrogen. Okay, so there's lots of hydrogens. 1, 2, 3, 4, 5, 6, 7. So we've got 7 hydrogens. Okay, so I'm kind of keeping track of how much I see. And then I need to go back and write left to right, hydrogen between nitrogen and oxygen. So we got to move this guy over here. So we have carbon. On our periodic table, it goes carbon, nitrogen. Then we're going to stick hydrogen right here between nitrogen and oxygen in our formula. Then oxygen. Okay, so we're close, and then we just have to go back and subscript these, which I don't think the online version subscripts. Okay, I'm not going to do this for all of them, but we should subscript those. Those should be subscripted. Okay, so that is our chemical formula for alanine. Okay, I'm going to copy, my text box. Okay, and then I have methionine. So I have these in the correct order. We just have to count them up. So let's see. So do I have carbon? Yeah, we have carbon. 1, 2, 3, 4, 5. Okay, they're different colors. That's confusing. So 5 carbons. Do we have any nitrogen? Oh, there's a nitrogen. We also have a sulfur. We have one sulfur, one nitrogen. Let's see. We have hydrogens. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens. That's kind of a weird number. And then oxygen. Yes, we have oxygen. 1, 2. Just 2 of those. Okay, just like that. Okay, so then we just have to make sure it's in the right order. So carbon, nitrogen. This one needs to be after hydrogen. And then, oops. We have to decide if sulfur or oxygen goes first. Well, sulfur is lower, so it's bigger. So sulfur goes first, and then oxygen goes next. So that would be our chemical formula. Again, these would need to be subscripted for that to be correct. So make sure you do that in Alex. All right, then these formulas. So this is tyrosine, cysteine, selenocysteine, and uric acid. So I will go ahead and do those really quick. Maybe I can put my text box over here. So CnHO. I can just write that out. I've got C and H fits between nitrogen and oxygen. O. And then I just count them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I think I have 9 carbons. Nitrogens. 1 nitrogen. Hydrogens. Let's start over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, another 11 hydrogens. And oxygen. 1, 2, 3. Okay, that would be the formula. Let's look at cysteine. So this one we have a sulfur, so we're going to add in sulfur. Where does sulfur go? It goes before oxygen. We also have nitrogen. Okay, that one. Oh, this one. Yeah, that one had nitrogen. Okay. Oh, and I don't have to put the number 1. If there's only 1, don't put the number 1. How many carbons? 1, 2, 3. How many nitrogens? Just 1. How many hydrogens? 1, 2, 3, 4, 5, 6, 7. So I'll fix that. And then 1 sulfur, 2 oxygens. So it might be helpful to have an example with a lot of elements on it. So on your on your note cards, so that you can remember which order they go in. So here we have selenium. Oh, where does that go? So selenium is right below sulfur. So selenium should go before oxygen. It should go after hydrogen. So we've got carbon. There's 3 of those. We have nitrogen. We have hydrogen. 4, 5, 6, 7. Same. And then this is just selenium instead. So we can just change that. Cysteine, selenocysteine. Okay. And then the last one is this uric acid. So do we have carbons? Yes, we have carbons. How many carbons? 1, 2, 3. Just 3. 1, 2, 3, 4 nitrogens. How many hydrogens? 1, 2, 3, 4 hydrogens. We don't have a selenium here. We have oxygen. 1, 2, 3. We just have to make sure we're counting correctly, putting them in the right order, and then these all need to be subscript numbers.